Hello everyone. Today we will be talking about the elastic constants of isotropic materials, and with this video we will be concluding the elasticity properties of materials. Now we have seen earlier the generalized Hooke's law, and we have seen the elasticity tensor, and we have learned that this elasticity tensor is symmetric, and therefore we have for an general anisotropic material, we have to define 21 elastic constants. And we have also said that for an isotropic material, the number of independent elastic constants further reduces to 2. And we will soon learn what this independent means. So let's look at the elastic constants of isotropic materials. We have already mentioned that for an isotropic linear elastic material, the number of independent elastic constant needed for a full characterization of material behavior is only 2. However, for elastic constants of isotropic linear elasticity have a clearly defined physical interpretation. And today we will be looking at these 4 elastic constants. In fact, we have already seen several of them, like we have seen modulus of elasticity, or Young's modulus. We have seen Poisson's ratio, which is shown as nu. And we have seen that both E and nu are related to stress-strain. Normal stress and normal strain, I should correct. Then we have seen modulus of rigidity, or shear modulus, that is represented as G. And we have seen G is found from the relations between tau and gamma, so shear stress and shear strain. And these are the 3 elastic constants we have seen earlier. And today we will be looking at modulus of compressibility, also known as bulk modulus and represented as K. And we will soon learn how this K is related to stresses and strains, or which types of stresses, which types of strains. Now, if we were to make a brief review again, in our previous slides we have seen the modulus of elasticity, how it is being defined, and we concluded that during the uniaxial loading of a material, the modulus of elasticity determines the elongation or shortening along the loading axis. So if we have a uniaxial tensile loading like this, if we stretch this with a force, the modulus of elasticity is responsible for the elongation along this loading axis. And it has a unit of newtons divided by meter square, or pascals. But since it's a big number, we often express that in terms of gigapascals. Another constant that we have seen earlier is Poisson's ratio. And Poisson's ratio is represented as nu and is defined as the ratio of transverse contraction strain to longitudinal extension strain in the direction of a stretching force. So if we were to pull this isotropic elastic material along its loading axis, it will be extending along that loading axis, and transverse it would be contracting. And therefore we have defined Poisson's ratio as minus transverse strain to longitudinal strain. So in this case, like, longitudinal strain is positive and transverse strain is negative, so we are in this zone. But if we were to, instead of stretching, if we were to compress this material, then the longitudinal will be minus, so we are in this zone, and the transverse strain will be extension, so we are in this zone. And together with this modulus of elasticity, Poisson's ratio determines the, again, elongation or shortening of a material, not longitudinally but transfers to the loading axis in uniaxial loading, and it's a dimensionless number. We have already seen this. And again, we have seen the third elastic constant, which is G, or modulus of rigidity, or shear modulus. And G determines the distortion of a material when subjected to a shearing stress, and it has a unit of, again, newtons divided by meter square, or pascals, and often expressed in gigapascals. So it's again a big number. So finally, our fourth elastic constants, which is represented as K, answers or gives us the answer of this question. What happens when a material is subjected to a triaxial compression? What is triaxial compression? Like this problem. We have a cubic material, let's say, and we are compressing it from all these three axes with a stress. Let's say this is hydrostatic pressure, so they are all the same. And when this material is subjected to these compressive stresses, it will shrink to this dashed line. So let's say that the initial volume is V0, so this blue material has an initial volume of V0, and the yellow will have a final volume of Vf. So what's the change in volume? It is delta V. Delta V is the change in volume, which is final volume minus the original volume, the initial volume. And note that this will give you a negative number. So pointing out that it is the volume change is negative, meaning it's decreased in volume. And note that these compressive stresses are often expressed as with a negative sign. So over here we have to define another stress term, and which is termed as the average stress. So the average stress is the average of the three stresses applied along three principal directions. So if you have three principal directions, sigma 1, 1, sigma 2, 2, sigma 2, 3, 3, we average them, divide them by 3. So in this question, for example, sigma plus sigma makes 3 sigma, divided by 3 will give us sigma. Note that this is, again, should be a negative sign, but since I am showing it over here, I don't put that negative sign. Anyhow, if you were to plot now the average stress to delta V over V0, which is, we can label it as volumetric strain. K can be defined as the slope of this line. So we can write this equation then, sigma average equals K times delta V over V0. And over here, K is known as modulus of compressibility or bulk modulus. So this is the fourth elastic constant for an isotropic linearly elastic material. So what are the constants again? Let's remember. Sigma equals modulus of elasticity times strain, longitudinal strain. Tau, shearing stress, equals G times gamma, shearing strain. And sigma average equals K times delta V over V0, which is volumetric strain. So normal strain, shear strain, volumetric strain. So if we were to look at, these are the stress terms: normal stress, shear stress, volumetric stress, let's call it, or the strain terms: normal strain, shear strain, and volumetric strain. And what are these? These are the elastic constants. Again, normal, shear, and volumetric terms. Now, if you were to solve a problem, I will try to explain them with a problem. Let's say that we have a material with unknown material properties, And let's say that this is a cubic material. So all these dimensions are 100 millimeters before we have applied any load. So before loading, this is the geometry. Now, this material will deform under uniaxial tension. So in this case, we are applying a load along the z-axis. So we are stretching this material along z, as shown over here. And as a result of this force, by the way, which is equals to 100 kilonewtons, this material will deform, or it has deformed. To what type of a shape? Again, a prismatic member. The length became 101 millimeter, and transverse dimensions have reduced to 99.6 millimeters and 99.6 millimeters in y direction. So for this problem, we need to determine the elastic constants, which is responsible for these length changes along the loading axis and transverse to the loading axis, which are modulus of elasticity and Poisson's ratio. So how are we going to solve this problem? Well, I will show you how to solve it by several ways. First of all, let's calculate the stress. So in this case, the stress is applied on this on this plane, which is a z plane, and it is acting along the z direction, so it's called sigma zz. So what's the force? 100 kilonewton, I can write it as 100,000 newton, divided by 100 times 100. What's that? 100 times 100. So this cross-sectional area. So I'm dividing to the original cross-sectional area. So if you were to conduct this, you will get 10 megapascals. Note that dividing Newton to millimeter square will yield directly a megapascals. Anyhow, how about the normal strains? In this case, the strain along the z-axis. So it is delta divided by L0. What's delta? Well, it's how much it extended. So final length, which is 100 or 101 millimeter, minus the original length, 100, divided by the original length, which is 100. If you were to make this, you will calculation, you will get 0.01. So what is modulus of elasticity? Well, modulus of elasticity is responsible, in this case for this uniaxial loading case, is responsible for this length change. So the stress 10 divided by strain 0.01 will give you 1000 megapascals or 1 gigapascal. This is relatively a low number, believe me. Now, how about the Poisson's ratio? To determine the Poisson's ratio, remember, we need the transverse strains. So in this case, obviously, this is an isotropic material. Why? Because from 100 millimeters and 100 millimeters, it turned out 99.6 and 99.6 millimeters. So the same. So therefore, delta xx equals delta yy, which is delta over L0, LF minus L0 divided by L0, 99.6 minus 100 divided by 100 will give you now a minus 0.004. And how is Poisson's ratio determined? Remember, it is determined as minus transverse strain divided by longitudinal strain. So transverse strain is this number over here, minus 0.004. And longitudinal strain is this number over here, 0.01. If you were to divide this, you will get 0.40. So, now, we can also solve the same problem using the constitutive relations of an isotropic material. And we have seen those relations earlier expressed in terms of the principal axis directions. So These are the equations that we have covered earlier. Now, we will be using basically these equations, but while we are using those equations, we have to keep in mind that the stress terms, the stress tensor for this problem, or for this problem I should say, sigma ZZ equals 10 megapascals, and the other normal stresses are 0, meaning we are not applying any stress in this direction and in that direction. Then the normal strain along the z-axis is 0.01, and the transverse strains are minus 0.004. Now, using these equations, or using these numbers, and using this equation, we will be solving for modulus of elasticity and Poisson's ratio. So the first term, we can write epsilon zz, so along the z direction, the strain equals 1 over E, open the parentheses, sigma zz minus nu times sigma xx plus sigma yy. Then, plugging in these numbers, 0.01 goes in here, sigma zz 10 megapascal goes in here, minus nu times 0 plus 0, so sigma x and sigma y are both 0. So from here, you can solve for E, which is 1 gigapascals again. Now, using the second term, epsilon xx equals 1 over E, open sigma xx minus nu times sigma yy plus sigma zz. Now, epsilon xx, as you can see, it's minus 0.04, equals 1 over 1000. We now know modulus of elasticity. Sigma xx is 0, minus nu times sigma yy 0, sigma zz is 10. So from here, you can solve for Poisson's ratio as 0.40. Now, let's look at what's volumetric strain. We have said that, but let's explain that. So, consider a cubic specimen of unit edge length. So, this cubic specimen has a length of 1, let's say, a unit. What's the volume, initial volume? Well, 1 times 1 times 1 is 1. Now, let's assume that this is made by a linearly elastic isotropic material. So this slope gives us the modulus of elasticity. Keep that in mind. Now, if you were to subject this material to uniaxial tension, so if you were to pull this with a stress, the longitudinally we will get 1 plus epsilon 1, the strain along this direction, and the contraction strain 1 plus epsilon 2, and 1 plus epsilon 3. Now, what's the final dimension? Final volume. Well, 1 plus epsilon 1 times 1 plus epsilon 2 times 1 plus epsilon 3. If you were to make this multiplication, you will get 1 plus epsilon 1 plus epsilon 2 plus epsilon 3, and a whole bunch of squared and cubic terms of strains. Now, remember, we have mentioned, at least in this course, CE 241, we are dealing with small strains. So these strains are already small. What happens if you were to take the square of a small number or the cubic of a small number? They will be even more small. Then we can neglect these terms and we can say that the final volume can be expressed approximately as 1 plus epsilon 1 plus epsilon 2 plus epsilon 3, which are the normal strains in case of a uniaxial loading. Now, what is delta V over V0, which we said volumetric strain? It is Vf minus V0 divided by V0. Since V0 is 1, and we are subtracting this number from 1, so this 1 will cancel out. So the volumetric strain will equal to the 3 normal strains, epsilon 1, epsilon 2, and epsilon 3. So this is termed as volumetric strain. Now, when subjected to the sigma, the strain along the loading axis is determined to be, so using this stress-strain relation, the strain over here can be expressed as sigma divided by the modulus of elasticity. And therefore, we can say the epsilon 1 will be equal to the strain number. And we can also say that the transverse strain we can calculate using Poisson's ratio. So we can write epsilon 22 and epsilon 33 as minus Poisson's ratio times the strain value, the longitudinal strain value. Now, the volumetric strain now is the addition of these three. Remember, this number plus that number plus that number. So if we add them up, we will get strain times 1 minus 2 nu. So this is the volumetric strain. Remember, the average stress we can express as the three principal stresses. So sigma plus 0 divided by 3. So we will get the average stress as sigma over 3. And now sigma 1 is 1, sigma 2, sigma 3 is 0. I just write what we have found earlier over here. Now, substituting all these into sigma average equals the bulk modulus times the volumetric strain. See, sigma average is addition of 1 plus 0 divided by 3, so sigma over 3, equals K times the volumetric strain, which we have already found as epsilon times 1 minus 2 nu. So the addition of these three numbers, epsilon minus nu times epsilon, and again this number minus nu times epsilon. That's why we have 2 over here. So we have this equation now. Look now, if we were to express K instead of in terms of sigma and epsilon, we can rewrite this equation and take epsilon down here and 1 minus 2 nu down here. We can write sigma over E times 1 over 3 times 1 minus 2 nu. Hey, who remembers this equation? Sigma over epsilon. See, for a linearly elastic material, this is modulus of elasticity. Therefore, this equation can be written as K equals E divided by 3 times 1 minus 2 nu. So what does this mean? This means that if we know modulus of elasticity and if we know Poisson's ratio, then we can calculate the bulk modulus. So in other words, we have two independent elastic constants to define isotropic materials. If we know 2, we can express the other term. So for an elastic constants of an isotropic material, if we were to wrap it up, for an isotropic linear elastic material, the number of independent elastic constants needed for a full characterization of material behavior is 2. So if you know 2 of the elastic constants, you can calculate the other 2. So what are those physically meaningful elastic constants? Those are modulus of elasticity, Poisson's ratio, modulus of rigidity, and modulus of compressibility. So even though we have 4 of these, if we know 2 of them, we can calculate the other 2. And in the previous slides, I showed the derivation of this. So we can find how bulk modulus is expressed in terms of E and nu. Similarly, you can show that when you know E and nu, you can calculate G, or if you know K and G, you can calculate modulus of elasticity. So, what's compressibility in compressibility? For soft materials such as pastes, tissues, rubbers, and gels, the bulk modulus, K, in other words, is several orders of magnitude greater than the shear modulus. This indicates that these materials cannot be readily deformed under triaxial stress state. In other words, they can be considered incompressible. So, what do we mean by incompressible? For incompressible materials, see, incompressible, you cannot compress them. The volumetric strain is close to zero, and the bulk modulus approaches, therefore, to infinity. So, if you were to look at this expression, if for this expression you write sigma average divided by K equals delta V over V0, so if delta V over V0, if this term goes to zero, or for this term to go to zero, whatever the stress is, whatever the triaxial compressive stresses are, K will approach to infinity. A very big number. That means the material is incompressible. We can also express this incompressibility in terms of Poisson's ratio. Hey, remember this equation that we have just derived? Look at this now. If K is infinity, how can K become infinity? Well, obviously, if the Poisson's ratio goes to 0.5, then this will go to 0 and K will go to infinity, meaning that the incompressible materials have a Poisson's ratio of 0.5, and that's the limiting number for a Poisson's ratio. So in our next lecture, we will be covering thermoelasticity.